the peak power. We drop the peak power and we increase the pulse length. It looks very minimal. It looks like only 350 picoseconds, not much. But what matters here is when did the laser turn off relative to when the implosion stagnates and the yield is produced. We call that bang time. And proportionately, that is a large change. And to quantify it, the plot on the right shows you what the pressure was in implosions as we changed this time difference between when the laser turned off and when the bang time. And that we call colloquially coast time. So as we reduce this coast time, in this particular case, reduce it by 350 picoseconds, we expect the pressure to almost double. That's a large effect. And so that we think is one of the principal reasons for that. The good news is that there's room for further improvements. We can go to even smaller LEH. We can go to novel home designs. I'm going to show you that in a few slides. So that is the first thing that we did. The second thing is better capsules. So first, the state of the art was ignition scale diamond capsules had surface pits, high Z inclusion voids, but now they're almost completely free of those surface pits, high Z inclusion voids. So this is a material scientist type of slide. So before 2020 or 2021, we had pits on the outside of the capsule, and those led to instability growth, lots of pits. That led to, when you looked at the implosion at the end, this is an X-ray image of the implosion, all these meteors, what we call meteors, that's bad news because those are radiating and stopping ignition, probably induced by some of these defects. We can't give you one-to-one. And then if you look at a cross-section of the capsule, where this is the 75 micron capsule, this is the diamond capsule, you see these voids. So it's not very nice material, and inclusions, high Z inclusions. So this was clearly not optimum. The improved metrology we did allows us to find these defects. And so when we went to, in 2021, we were able to then remove these defects. And indeed, we have many fewer pits and voids. So
try to wrap up in 2 minutes so we can have some time for questions.
Absolutely. So this is what it looks like. When the shot goes off, you get a huge, this is just a camera picture of the optical emission. You see that everything gets very hot around it. You get plasmas blowing off. But let's look at some of the salient features of this shot, I think you'll like. First of all, we observed for the first time rapid hotspot expansion, even as the fusion output continued to increase. These are X-ray images in time over 100 picoseconds. And what you see, which we've never seen before, is when it reached minimum volume, it's emitting X-rays, but then it actually is emitting more and more X-rays as time goes on, even as exploding. That's proof that this alpha heating is just continuing to make fusion neutrons even after it's exploding. Very exciting for us. The burn width went down, went from a full width half maximum of 137 picoseconds, 98 picoseconds. That is also example of fusion burn exponentiation. This is where we get the power. This fusion produced 10% of the incident sunlight on power. And in terms of energy, though, it's much more modest. It's 79 kilovolt batteries, 1 hour house electrical power, or 1 gallon brought to boil. So lots of work to do. These are another way to show the metrics, the yield versus temperature. You see it jumping up by a factor of 2 with the yield, the inferred hotspot energy and hotspot mass going up. We're burning more of the fuel, and the burn width going down as the radius goes up. So again, all these signatures point to that. Now, what about the 2 repeats? We did 2 shots in November, October. The yield dropped. That indicates that there are variables that may still impact us in this new regime. And one of the main variables is what we call the mode 1. This is in simulation that shows that if you just have 2% higher drive on one side than the other, you greatly distort the capsule. You get much more shell forming at the top than the bottom. You get the hotspot moving. This leads to an inefficiency because you're not putting all your energy into hotspot energy. And this is seen in the ROR pictures. So clearly we have work to do to reduce this mode 1 or to make things more robust. And in fact, making things robust is exactly what we want to do. So what's next? We want to isolate the impacts, and we want to improve robustness and increase scale and compression for reaching 10 megajoule yield levels. And so the first thing is the smaller fill hole. This is what we've been using, laser drilled. We now have a focused ion beam drilled technique to reduce the hole mass deficit. We're actually going to try this Sunday. We're going to go to smaller laser entrance holes and smaller area to volume hole ROMs. Clearly a sphere has got the smallest area to volume, but this already gets you most of the way there. Smaller wall area, less losses. We can drive larger and thicker capsules. And can we compress things higher? That's a tall order for diamond. We'll find out, but we will try. If we can increase the rho R, of course, we can make things, the aero density, we can make the burn rate faster and increase the yield. And that's what this simulation shows. So to basically end here, with a wider community, this also sets the stage for potential new US program to explore inertial fusion as path for clean energy. And our National Academy of Sciences said in 2013 that the appropriate time to start a new broad-based inertial fusion energy program was when ignition is achieved. And we're very close to that. And so talks are already starting here to reinvigorate the discussions. And what is a inertial fusion energy thing has got going for it? Well, separable components, a driver, separable driver that can be modular, target, a reactor, and a balance-up plant. But it's a tall order. I just want to remind you that a gigawatt power IFE facility, before subtracting any inefficiencies, corresponds to 100 megajoules per shot, 10 times a second. That's tough. We're at a megajoule. I think we can get it 10 to 20, but doing it 10 times a second it would be a technological marvel with the economic constraints. But anyway, fusion energy offers a long-term vision for enduring global climate and energy security. And I thank you for your attention.
Okay, thank you very much, Otto. There's a couple questions on the chat, which I will ask the people to ask directly. The first is from Yitzhak Maron. And by the way, thank you, Yitzhak Maron, because he basically brought us together and brought Nino to the conference. So Yitzhak, if you want to unmute and turn on your camera, go ahead.
Yes.
Yeah, Nino, so my question is, do you know more details on the impurities that you really have at the capsule when you are getting the 1.4 megajoule on their amount, or what species they are?
Well, yes, we see tungsten lines because we have tungsten as a dopant in the diamond. We can't see carbon lines because it's too soft, but we do have tungsten. We have the fill tube brings in some tungsten. Let me see. Let me go back into full screen mode. So, sorry, wrong one. So that's a good question. So this fill tube jet brings in carbon and tungsten, and that's why it's brighter emission, but it's a small fraction of the total. Same here. This is bringing in tungsten and carbon. Now, there's also probably tungsten and inside the outside regions of the fuel. There's some indications of that. So some of the fuel is outside the fuel is probably being mixed with tungsten as well. That will limit how much you can burn up in the end. So does that answer your question?
Yeah, thank you. Thanks.
Okay, and then one final question from Yaakov Kreisik at the Technion. I'll just read it to save time. He thanks you for a great presentation, and I echo that.
Thank you.
Let me know what the initial stored energy was in order to drive the lasers. And also, yes, is there any problem with the target preheating by X-rays at earlier times of the shock implosion?
Okay, so the answer is, I believe our laser is about 1% efficient, so it's a 400 megajoule wall plug efficiency, way too much. We'll talk about, we have to get down to 10 or 15% efficiencies with new laser technology. So that's the answer to the first question. The second question, sorry, it's late. Can you just quickly remind me, give me one clue word on that?
Yes, is there any problems with the target preheating by X-rays
yes,
at earlier time?
Right, well, yes, that's what the tungsten is in there to shield the inside of the diamond from from X-rays. And we don't think that's much of a problem. We measure how many of those X-rays we have. So we don't think we don't think those X-rays, if they make it through the ablator, will not heat up the ice per se. What they will do is drop the density of the ablator near the ice and make it more unstable. So that is one of the things we're studying with focused experiments I couldn't go into in this talk. But yes, we are worried about how hard X-rays modify the stability of the target.
Okay, thank you very, very much. And thank you for
thank
being
you.
up at this ungodly hour on the West Coast of the United States.
We're used to it here.
Everyone, please stay tuned to the panel discussion that'll be at the end of our oral presentations. Nino will participate in that, and there'll be more opportunity to ask some questions about what the future of this technology might bring us.
Thank you.
So I'd like to call on our next speaker, who is Hank Strauss from HRS Fusion. Please turn on your your camera is already turned on. You're unmuted. You can go ahead and share your screen. And Hank will talk about the solution of the disruption problem in ITER. And you'll tell us what ITER means very first.
Okay, fine. Okay, so ITER is called the International Tokamak Experimental Reactor. It's a big experiment under construction in France. First of all, you can see my slide, right? You can see this visible? Okay, so
yes.
All right, so many times just like instabilities can be a problem in inertial fusion, as we heard in the middle of the last talk, they can also be a problem in tokamaks, which are a different approach to fusion, magnetic confinement. And occasionally these produce disruptions, and the disruptions are kind of large-scale instabilities. And in present experiments such as the JET, which is the Joint European Torus, which is the largest experiment at present, they can cause a thermal quench, which is the sudden loss of all the thermal energy in the plasma in a time of a millisecond, which is a forever compared to inertial fusion, but it's a very short time, and it's not a problem in JET, but if it's scaled up to this large ITER experiment, which is much larger and going to be much higher power, then it'll produce too large of a heat flux. And so to deal with this disruption problem, they have a plan in ITER to inject massive amounts of material to radiate the energy so it doesn't cause melting of structures surrounding the plasma. But a strange problem is that even though this disruption's been known for a long time, they still never quite figured out what it exactly is that's producing the disruption. So that's my topic here. And so let me show you these two pictures are data from a particular shot on the JET experiment. So on the left, you're seeing the time history of a certain kind of disruption. The green is the temperature inside the plasma, and the purple is the magnetic field measured outside the plasma. So it stays constant for a while, then there's this kind of relatively slow drop of the temperature and then a fast drop. And it's similarly with the magnetic field, there's an increase of magnetic field that coincides with this drop. These are magnetic perturbations associated with instability. And then there's this sudden spike. So the spike has been around a long time. It's always there, and people didn't really know what it was. So there's two parts of the disruption. There's a precursor, which is this part, and then there's this fast thermal quench part. And this is a separate MHD instability, and I'm showing it expanded in time in the second plot. You see it's a nice, smoothly growing instability. It grows up, comes down. This is the temperature. The temperature drops during the growth time of this instability. Okay, so I've shown through analysis and some simulations, which I'll briefly sketch in the next slide that this is a certain kind of instability. It depends on, it's like something called a tearing mode, which is well known in plasma theory, but it's a version of it that depends on the magnetic shell surrounding the plasma having a certain resistivity, a certain time for magnetic fields to penetrate through that shell, which is called the resistor wall magnetic penetration time, which I'm calling tau wall. And that gives a certain kind of instability in which the growth rate depends on that penetration time to some fractional power. Now, since ITER has a much thicker, much better conducting shell than JET, and that was by design, actually. It's like 50 times longer, and so therefore, this instability is much slower. So this spike will be greatly spread out. In fact, it might not have a very serious impact on, well, it'll have a serious impact, but maybe not as bad as they thought. So this is just an example of many simulations I've carried out. This is for an ITER example. So this is with my code, M3D code, particular ITER case. These are cross sections on the right through the cross sections through the torus, showing the pressure perturbation, the pressure, total pressure. So on the left, I've shown how the thermal quench time depends on the resistor wall time. In the simulations, I can vary this wall time. And so when the wall time is fairly low, then you can see that the thermal quench time is going up rapidly. It can be fit by this same power law that you would get from the theory that I just mentioned. So this is this growth with the resistor wall time, the 4/9 power actually, and then it asymptotes. So the JET experiment is located in this regime here, where S wall is relatively low, or tau wall is relatively low, and then this dark line shows where JET is going, where ITER is going to be. So they're very different. And if you look at these non-ITER simulations, you can see that the behavior during the is very different, whether you're in the JET regime or the ITER regime. In this case, there's a lot of advection and there's a lot of distortion of the pressure. And here, there's mostly a much slower kind of process going on. Okay, so there, if you use these simulations and you also use the analysis, then you can make predictions of what will happen in ITER. So the theory and analysis shows that the thermal quench time is the shorter of these two kinds of time. One is this growth time of the instability, which I showed you before, or there's like when you were in this case that was independent for large wall time, you get something which I'm calling tau parallel here, which is diffusion along the magnetic field given by these magnetic perturbations. So this is like a kind of, the magnetic field kind of becomes stochastic, and there's transport along that perturbed magnetic field, and it's given by this tau parallel. So this is a well-known effect. And so I can calculate this, and I can also compare it with the growth time of the mode. So I should mention that this time is strongly dependent on the temperature as well as on this magnetic field perturbation strength. So I don't know exactly what those are going to be in ITER yet, but so I've made a plot. I've plotted the thermal quench time versus what the edge temperature would be, and I get different values of this thermal quench time. So that's what's being plotted here. This is where JET is. This red line shows that JET has a very short thermal quench time. It's down here, and it's limited by the instability. In ITER, the instability is way up here, so it's not going to have a serious effect on limiting the thermal quench time. Instead,
1 minute,
this
Hank.
this parallel diffusion, and I've given two examples with two values of this B parameter taken from the simulations and also from a scan of experimental results. So So therefore, it's very possible that you can get in a regime where to summarize that, instead of having a thermal quench time of a millisecond caused by this resistor wall tearing mode, which I showed, you could have an ITER thermal quench time, which is almost 2 orders of magnitude longer, caused by this precursor. And that would really make a very big difference in how you would have to deal with ITER disruptions. If anyone's interested in more results, of course, you can ask me a question if there's any time, but I've got these 2 recent papers that appeared in Physics of Plasmas. And then I'll continue with other work. No need to mention it now. So, okay, so thanks for your attention. And
okay, thank you, Hank. We have time for maybe one question. Are there any questions? If not, I have a quick question.
Sure.
Okay, so the instability will be slower, maybe less serious. Is there something that can be done to eliminate the possibility of the instability altogether?
There probably are, but those involved, I just don't have time to discuss that. There have been ideas for how to prevent the instability in the first place. It's usually prevented by the rotation of the plasma in jet. That might not be effective in ITER. There's other schemes for, injecting microwaves that can also, for a reason I can't go into now, slow down or prevent the initial instability. So there are strategies, but that's really the topic of another talk, I guess.
Okay, thank you very much. Kindly unshare your screen and mute your microphone. And Hank will participate in our round table discussion at the end of this session as well. So stay tuned for it. I'd like to introduce our next speaker, Nir Drucker from the Technion, who will speak on enhancement of plasma-assisted ignition by multi-voltage pulse discharges. Here we go, talking about ignition again, but a very different kind of ignition.
Yeah, a very different kind of ignition. Thank you very much. So this talk is basically about some of my PhD research, which was supervised by Professor Barry Greenberg, Professor Ansher, and advised by Dr. Gideon Goldwine. I just wanted to mention that. Now, okay, so just a bit of a background in a nutshell on plasma-assisted ignition combustion. So this field is basically heavily investigated in the past 2 decades or so, and it shows an improvement in ignition combustion processes. For example, increased heat release rates in internal combustion engines and increased ignition kernel radiuses. Now, much of the improvement is associated with the enhanced oxygen radicals generation, and that's mostly because of electron impact reactions. Now, in this research, we're trying to see if we can efficiently control cold plasma processes, which enhance ignition. And by that, basically, we mean that if we can evaluate energy deposition into specific gas modes, and if we can enhance those energy deposition into those specific modes, and here we use a theoretical numerical investigation. So just a bit about the scenario or system we're considering. We're basically considering the application of bipolar voltage pulse as a source, which is repeatedly applied for different pulse repetition frequencies or PRFs. And we do that over the electric barrier electrode arrangement, as you can see here, and which encloses a low pressure air, about 8 kilopascals. And that allows us to use an evaluation of a 1D drift diffusion model, which includes 24 species, electron energy density, 168 kinetic reaction scheme, and etc. Now, there are a lot of phenomena that occurs there, but I want to focus for this talk about, let's say, 2 of them. I wanted to consider or to focus on the discharge coupled energy during each of those pulses, and the energy deposition in specific mode, as we said, but especially obviously the oxygen radicals generation, the energy which is deposited in the oxygen's radicals creation. So this is basically what we see here. This is just one type of result that we did. So we see here basically the time evaluation in each one of the discharge or cases with different repetition frequency varying from 40 kilohertz to 1 megahertz. The 40 kilohertz is the black lines, the 1 megahertz is the blue line. You have some different colors in between. And we can see the variability. For example, let's start here. We can see that the initial electron density increases with PRF, with the pulse repetition frequency. can actually better see this thing. Peak electron density decreases with the pulse repetition frequency from the black to blue. And about the voltage, the breakdown voltage decreases with the pulse repetition frequency. And the secondary voltage peak here increases with the pulse repetition frequency. Now I want to concentrate on the second figure from the top, which I think personally it's a bit more interesting, is that we can see that the energy, this is the energy deposition, this is the coupled energy over time. And we can see that the energy deposition entering basically in steps, let's say we call them QP1 and QP2. That's like the two major steps here. And they are separated by points in time or the gap voltage, and therefore the coupled power are vanished. And we can see here that QP1 is relatively constant in the variety of the PRFs, but QP2 rises with the PRF. And that means it rises with the secondary gap voltage magnitude. And right after 40 kilohertz, we get to the point where QP2 is larger than QP1. Now, I think it's important to mention that relatively the same trends were observed between consecutive pulses when you consider only few pulses. And another thing is that QP2 larger than QP1 basically means that you get a higher energy deposition at lower voltages, because during QP1, this is the breakdown voltage, the voltage is higher. So there's quite a lot of coupling, but I want to briefly discuss two of them. So first one is the gap voltage magnitude and the electron density relation. I'm not going to get into specifics, but this is basically a typical behavior of this DBD arrangement with the time varying voltage source. Eventually, what we get is that if the initial electron density increases with the pulse repetition frequency or the discharge number, then we get a lower breakdown voltage or the breakdown voltage decrease. We get a peak electron density decrease, but a secondary voltage pulse increase. Now, sorry. To the other part, which again I think is a bit more interesting, is the higher energy deposition at lower voltages. So why does it happen? So if you consider that the coupled power is mainly the electron joule heating term, so we can say it's proportional to the electron density and the square of the gap voltage. Now, we can see here the fourth pulse 1 megahertz case. In normalized case, we can see all the square related quantities. So in blue, we have the electron density. We can see is initially relatively low. Then it's getting higher obviously during the breakdown voltage pulse, which is in red here. But actually, it lags behind it in time. So what happened is if we look at the coupled power as a pulse, which is the purple curve here, we can see it is relatively narrow. But when we get to the secondary voltage pulse, which is lower in magnitude, we already have quite a lot of electrons because of the first breakdown pulse. So eventually we get a much wider coupled power pulse, which leads to higher energy deposition. This is the green here, higher energy deposition step during the lower voltage pulse. So after discussing the coupled energy, we want to see how it transfers to different modes, and especially to the generation of oxygen radicals. So the dominant path for oxygen radicals in those systems is, first of all, electron impact dissociation of oxygen, but even more importantly, the quenching of nitrogen, of electronically excited nitrogen. So, and those are actually obviously created by, again, electron impact reactions. So these are like the main two energy channels or paths that we are following. They are related. And we made quite a lot of evaluations for each of the 4 consecutive pulses of the 40 kilohertz to 1 megahertz repetition frequencies with the same voltage source that we've seen that we used in the previous slides. We call it IVS-1, but we also had another 8 additional consecutive pulses with 110 kilohertz frequency, repetition frequency, with another voltage source called DS2. You can see the difference between them. Basically, DS2 has higher magnitudes. So when you plot that of those energy channels, the energy that channel to electronically excited nitrogen, which you can see here in purple, and eventually the energy that was deposited in the generation of oxygen radicals.
Here, 1 minute.
Yeah. So basically, you can see that you put it against energy channel, those energy channels against coupled energy. You can see that the energy deposition in those channels is linearly dependent on the coupled energy, which is quite interesting. But also there's a trend difference between VS1 and VS2, and apparently this is due to a competition between the nitrogen electronic excitation channel and the vibrational channel of oxygen and nitrogen during the secondary pulse. So this is basically a statement in the conclusion of what we've seen so far. The last thing I just said basically comes because of the energy distribution between channels, which it depends on electron energy. And it depends on electron energy, it depends on gap voltage. So we also thought about a different scenario of having like a very low voltage, relatively low auxiliary voltage pulse, when we already have those electrons, but the magnitudes are set such that the nitrogen electronic excitation channel will be more active, and we got a pretty much better results, which we can't really discuss right now. But those two channels, for example, which were important for us, they got 60% of the total coupled energy, which is much more. And that's it basically. And even the oxygen, the channel of the oxygen alone now is larger than the vibrational channel. So that's pretty much what we wanted to achieve. That's it basically.
Okay, thank you very much. I don't think we have time for questions. So if you have questions, please write directly to Anir, and I'll have to move on to the next talk. The next talk is by, please unshare your screen.
Yeah.
And thank you very actually, it's very interesting, and I'd like to talk to you about it later.
I would love that.
Okay, good. Thank you very much. The next speaker is Yang Cao from the Technion, and he will speak on the nonlinear high-power microwave complete absorption phenomena in a plasma field waveguide. Take it away. Yang, you have to unmute. We're not hearing you.
Yeah. Hi. Hello, everyone. Hi. I'm Yang from Technion, and it's a great honor for me to share our recent research regarding the topic of the nonlinear high-power microwave complete absorption phenomena in a plasma field waveguide. And this work is collaborated with Jean Leopold, Yuri Blioch, Guy Lebovich, and Yakov Krasik. So in this research, a super radiant backward wave oscillator is used as the microwave source. This BWO is driven by a high voltage pulse generated by an all solid state opening switch based generator, given a pulse with voltage of 350 kilovolt, current 2 kiloampere, and a 5 nanosecond pulse duration. And this high voltage pulse is measured by the capacitive voltage divider and Rogowski coil, which is located at the cathode holder plane. And this high voltage pulse is applied to a graphite hollow cathode with sharp edge, and the electron is emitted at the sharp edge due to by the explosive emission and propagating in the slow wave structure, and guided by an axial magnetic field, which generated by our solenoid with the amplitude of about 8 Tesla. So the generated microwave pulse is emitted in the horn antenna over here. And this is the typical pulse we measured at the output. And this high power microwave source give us the power of the microwave about 1.2 gigawatt and the duration of 0.4 nanosecond with frequency 25.5 gigahertz. So for this specific experiment, we applied the output of this microwave source without the horn antenna directly to a cylindrical waveguide, which connected to the flashboard plasma source and propagating in the cylindrical waveguide inside. And in order to create the plasma interaction with the high power microwave, we have this section with the opening slits in the cylindrical waveguide in order to make the flashboard to fill this waveguide to interact with our microwave. There are two loop type directional coupler installed at the entrance and also the exit of the flashboard tube to monitor the incident and the transmitted microwave pulse. And the first coupler could also measure the reflected pulse. in these experiments. And this is how it's look for our directional coupler. So the flashboard plasma source is characterized by different diagnostic methods, such as visible spectroscopy, single lambda probe, microwave cutoff, and the visible spectrometer. And these measurements shows a good agreement between each other. And therefore, we could control our preliminary plasma density by shooting the microwave pulse at a different time delay in respect with the beginning of the flashboard discharge. Also, we use the fast framing camera to observe the plasma light emission, and it shows a good uniformity in both the axial and radial directions. So to measure the energetic electron, which created by the microwave and the plasma interaction, we use the optical fiber which shielded with a copper tube with different thickness aluminum foil covered at the fiber end, which serve as a filter to filter out the electron with energy not enough to penetrate this aluminum foil. And the energetic electron penetrate this aluminum foil filter, striking the plastic optical fiber and generating the fluorescence which detected by the photomultiplier tube, which directly connected to the fiber. And by such way, we can measure the energetic electron with a filter. So in our experiment, the fiber detector is installed at the side of the microwave plasma interaction region, where we have this opening slots waveguide. And also we install the detector at the downstream of the interaction region facing axially towards the microwave incoming direction in order to observe the axial accelerated electrons. So here is the normalized photomultiplier tube signal, which measuring the light emission induced by the fast electron at the side and at the front fiber. We have made this experiment in different plasma density and also with different thickness of the aluminum foil. You could see clearly that the energetic electron has been ejected from the plasma in both radial and longitudinal direction with energy up to 70 kiloelectron volts. Also, the different plasma density for different preliminary plasma density, it shows different time delay of the observed energetic electron signal compared with the microwave entering the flashboard plasma tube. And this could relate to the microwave behavior at the near critical density plasmas. We measure the incident and the transmitted microwave pulse at the different preliminary density plasma, and the reflected pulse, as I mentioned before, could also be measured by the first coupler, which located at the entrance of the flashboard tube. So for the vacuum case, which is over here, we could see clearly that the incident and the transmitted microwave appears and without the presence of the reflected pulse. And the transmitted microwave pulse is smaller compared to the incident one due to some loss in the waveguide. And at the plasma density 310 to 12 per centimeter cubic, the transmitted microwave pulse is smaller compared with the vacuum case. And if we look at the case of 810 to 12 per centimeter cubic plasma, we don't see any transmitted microwave, but with a strong reflected signal. And the most interesting case that in the plasma density range of 510 to 12 per centimeter cubic, there is no transmitted and almost no reflected pulse has been observed. And if we make the summary plot of the transmission and the reflection coefficient at a different plasma density, we could find out at the range of 510 to 12 per centimeter cubic, the transmitted and the reflection coefficient both close to 0, which means all the microwave energy has been absorbed by our plasma. In addition, we use the three-dimensional LSB simulation to simulate what is happening in the case of the complete absorption happens, and the microwave is entering our plasma, and the group velocity is decreased close to 0 because this is near the critical, and gradually all the power has been absorbed. Let's take the case.
Yang, 1 minute, please.
Oh, okay. let's take the simulation result in different plasma density. We calculate the energy of the electron and the microwave field energy, and also the number density of the electrons. In the case of 4×10⁻12 per centimeter cubic, we see clearly the microwave pulse transmitted without the power loss. And in the case of 8×10⁻12 per centimeter cubic, we see almost no transmitted and a strong reflection. But in the case of 5×10⁻12, we see a lot of energy of the power has been transferred to the electron, and there's almost no transmit and reflection pulse. So if we compare the simulation and the experimental result, you can see the solid line shows you the simulation, the dash line shows you the experiment. It shows a really good agreement between the simulation and the experiments. So what happens in the plasma actually? The microwave kicks part of the electron to the waveguide wall due to the point-motive force, causing the formation of the positive potential well in the waveguide. And the remaining part of the electron oscillating in this potential well, high power microwave pulse absorbed when the group velocity of the pulse approaches to 0, and the pulse have enough time to transfer energy to the electron, which captured by the well due to the electron ion collision. And this is a nonlinear effect that only occurs when the microwave power is high. And that's the conclusion. And I think my time is up. Thank you.
Okay, thank you very much. We have time for one question. Anyone have one? If not, I do. Okay, I'm not hearing one, so I'll ask my question. You showed a slow wave structure, but it wasn't clear to me whether this was a slow wave structure for the microwave, which is what I would expect, or whether it's somehow or other affecting plasma propagation. And connected to that question is, what is determining the frequency of the microwave emission?
Okay, so this is actually from the generation of this microwave. So our electron beam with some certain velocity, which is defined by our high power, high voltage pulse, and propagating in this slow wave structure. So the duration, the frequency of this microwave actually defined by this interaction time of this slow wave structure curvature, which have the boundary over here. So first, this is designed specifically for this voltage, I mean this slow wave structure, in order to produce this frequency. And the second, if you want to change it, first you need to change the curvature, of course, and also the velocity of this electron should be synchronized or should be designed specifically, I mean confirmed by the simulation to see what is the frequency output.
Okay, thank you very much.
Yeah.
Please unshare your
problem.
screen and go on silent. And I'll call for our next speaker, Marco. Wow. Not sure if I'm going to pronounce it right. Go ahead, pronounce your name.
Marco Cveic. Hi, good morning.
Good morning. And Marco will speak about spectroscopic measurements of the magnetic field curvature and self-rotating plasma.
Yes, good morning. Thank you. So in this talk, I will describe a novel polarization-based spectroscopic technique to directly measure the magnetic field curvature. So in this slide, the principle of experiment is depicted. As you can see, we have a Z-pinch source. The main difference from a standard Z-pinch without pre-embedded axial magnetic field is that in this case, during the implosion, not only plasma is compressed, but also the axial magnetic field. And this profoundly affects the magnetic field distribution, the pressure and energy balance, and the implosion dynamics. So in order to characterize things, you need to know the magnetic field distribution and also direction to understand the plasma dynamics, which is governed by the J cross B forces. The magnetic field distribution is the only way to obtain the current density distribution. Also, this experimental geometry is very important to maglev approach of nuclear fusion, as mentioned earlier, but also is a unique platform to study phenomena that are related to high energy density physics and to laboratory astrophysics. In this slide, I'm showing the experimental details of the experiment. The spectroscopic diagnostics setup is unique because we are using 3 spectroscopic systems to look plasma from 3 different radial directions with a high spatial, spectral, and temporal resolutions. We can simultaneously measure 6 quantities, which are denoted here. So we can measure all 3 spatial components of the magnetic field: azimuthal, axial, and radial. We can measure azimuthal velocity v theta, implosion velocity VR, and also we can measure plasma parameters. With this slide, I want to explain why and how to show how the curvature of magnetic field is created. So basically, during the implosion, we have that the busy flux is compressed with the imploding plasma. However, at the electrode, busy lines stay frozen at their initial radius. They are trapped into the electrode. Thus, a transition region occurs, and busy field lines are bent radially inward. So to measure BR, we have a spectroscopic setup, and this spectroscopic setup for BR determination is basically the same as for B theta measurements. It can separate the left and right hand circular polarized plasma emission due to the Zeeman effect using the quarter wave plate and the polarizing beam splitter. The plasma emission is firstly focused, then the quarter wave plate converts the right and left circularly polarized plasma emission to orthogonal linear polarizations. Then the orthogonal linear polarizations are separated by the polarizing beam splitter, and then we focus to legs or ends of the bifurcated linear fiber array, which are designated here as RHC and LHC channel. The plasma emission of the joint end of the fiber array containing RHC and LHC plasma emission is focused on the entrance slit of the imaging spectrometer. Now, from the same spectral recording used for B theta determination, for the BR determination, we use an integration chord that is parallel to B, that is line out at y equals 0. Now, in the following slides, I will explain the BR measurements idea and how the complex line spectrum is deconvolved. So, for the line of sight that goes through the plasma center, parallel to plus BR, we observe sigma plus and sigma minus Zeeman components in RHC and LHC channels respectively from one side of the plasma channel. So basically, this is the same as the idea behind B theta measurements. Now, because now we are having 2 sides, we are looking through the plasma center. We have two plasmas, one shell, one part of the shell approaching and one part of the shell retracting. Now, from the other side of plasma shell, parallel to minus BR, we observe sigma plus and sigma minus Zeeman components, which are now shifted in the opposite direction than the ones observed due to the plus BR. At this stage, in RHC and LHC channels, we would observe and record the same overall line shape composed of 2 shifted sigma components. However, the plasma implodes, and this is the main point. This means that the Zeeman components coming from the opposite sides of the plasma will be Doppler shifted. The components coming from the part of the shell that retracts will be red shifted, and in contrast, the components coming from the shell that is approaching will be blue shifted. Thus, spectral line shapes in the RHC and LHC channel will have different appearances. Now, to demonstrate this more clearly, the sigma plus components from plus BR and minus BR tend to become more distant from each other, while the sigma minus components tend to become a single line. The difference between the shapes of RHC and LHC channel yield the value of BR. And this is recorded. BR, the radial component of the magnetic field due to the field curvature, is measured for the first time. The spectral recording on the left shows a chordally integrated emission of the oxygen 6 line at 3,811 angstrom. The experimental line shapes shown here on the graphs are taken from the lineouts marked with the white rectangles shown on the spectral recording, and these rectangles denote the lineouts at y equals 0. Using the advanced line shape modeling that includes also the influence of other B components, BZ and B theta, the difference in the RHC and LHC shapes yields a BR value of 2.2 Tesla. The importance of BR determination is that it produces the rotation due to the JZ cross BR and affects the implosion in plasma near the electrodes. This will be illustrated on the next slide.
1 minute.
Yes, great, thanks you. So thanks to simultaneous measurements of the azimuth magnetic field, plasma parameters, self-generated rotation velocity, we can estimate the following from which you can see on the screen. Using the equation of motion for theta direction, we obtained that calculated V theta is similar to the measured value. Thus, BR can cause the measured rotation velocity due to the J cross B force. That would be all. Thank you for your attention.
Okay, thank you. Is there a question for Marco? I have a question.
I have a
Yes,
short
please.
question.
Go
Yes.
ahead, Yakov.
Marco, can you say me your estimates regarding diffusion time for magnetic field and the initial distribution of your axial magnetic field, which also should be non-uniform?
Yeah, because we are using pretty much big coils. BZ axial distribution is pretty much uniform over the volume which plasma implodes, and diffusion times I didn't calculate, but they should be pretty fast. Plasma here is the Reynolds number is high.
If it is pretty fast, it will be not frozen.
It's pretty low, so it's but the Reynolds number is high, so plasma the magnetic field is frozen in the plasma also.
Okay, I have to cut it
Thank
off
you.
now. Thank you very
Okay,
much,
thanks.
Marco. Yakov, thank you for your question. Please remove
Yes.
your screen. Great. And I will share my screen, maybe, if I figure out how to do it. And I'm going to call. No, we still have one more talk. Excuse me. Just a second. I'm going to call on Sharon Bachman, who will speak to us on estimated adhesion of boron carbide coatings on aluminum substrates. Sharon, take it away.
Right. So, yes. So in this is the topic I will talk about. A boron has a big cross section for a neutron absorption. Neutrons that are absorbed by a boron produce two energetic particles, while gamma photoemission occurs in 94% of the reactions. Boron is a difficult material to process, and therefore it is not commercially available. For this reason, boron compounds comprising carbon and nitrogen can be used. And the advantage of using carbon is the higher amount of boron atoms per one carbon atom. So our goal is a strong and durable attachment of a boron carbide coatings on aluminum substrate for neutron detections. Boron carbide and aluminum are two dissimilar materials, and therefore it is a highly challenging task. The challenges are the formation of the aluminum carbon bond, which is unstable in humid environment, and different thermal expansion coefficient, which may cause stress and a subsequent adhesive failure. So our strategy is to apply a sort of a buffer layer to prevent the formation of the aluminum carbon bond, and to provide a gradual change in the thermal expansion coefficients. The deposition of the coating was carried out in a vacuum chamber by a magnetron sputtering technique driven by a plasma formation. The chamber contains a set of two magnetrons, and a bias power supply connected directly to the substrate and assist to obtain improved coating properties. So the coating process includes 3 sequential steps. The first step is surface cleaning activation. The second, the position of the titanium interlayer, that it is an adhesive layer that prevent the contact direct of the boron carbide coating to the aluminum and provide the gradual change of the thermal expansion coefficient. And the last step is the boron carbide coatings. We investigated the bias supply, the coating durability over time, and the effect of the titanium interlayer thickness. So first, we investigated the structure and morphology of the coatings that were prepared or synthesized under different bias. And it is clear that the bias affect the morphology. And this is because of the enhanced ion bombardment of argon ions that cause a resputtering. We perform here a scratch test, and we can see a strong adhesion for a coating that prepared under bias of 60 to 145, while for the 205 volt, we can see that part of the coating was detached, and it was done immediately after when we took out the substrate from the deposition chamber. We can also see that these peelings expose the aluminum substrate, and we attribute it to stress developed during the process. The structure of the coating is amorphous, and based on the XPS measurements, we can see that the main peaks are typical peaks for boron in a B4C composition. And we can see also, okay, it's very difficult for me to show, but when we increase the bias voltage, we can see that there is a bump created or a shoulder, and this shoulder represents oxide species on top of the surface. And this oxide species can easily remove by short sputtering. We also follow the coating durability over time. All coatings were stored under a 2% relative humidity. And after 6 weeks, you can see that the coating that was prepared under 145 volt peeled away. And you can see that, that the titanium and the aluminum exposed. After 20 week storage, the 60 and 100% remained still fully adhered to the substrate, but after 9 months, we saw that the peeling started flaking off the surface, the coating started flaking off the surface. And this was taken today, and you can see that the coating that prepared under the 60 volt bias voltage remain fully adhered until today, after 2 years from the process. And you can see here that, at the 100 volt, only the titanium exposed and not the aluminum. So we attribute it to a different mechanism or stress relief over time, or oxidation over time. And we also probe the effect of the titanium interlayer. So I just show it fast. So we prepared a boron coating on a thick interlayer, on a thick titanium or on a thin titanium, and you can see the result after 1.5 years. A thick boron coating on a thin titanium layer remained fully adhered to the surface. How much time do I have?
You have another minute. If you end right now, it's also okay.
Okay, yeah, I will.
1 minute.
What I want to show, okay, what I just want to show you here, that increasing the bias allows, increasing the titanium layer allows thicker boron carbide to attach efficiently to the substrate. So these are the conclusions. I just want to say one thing. The following causes mechanism mainly affect the adhesion. That's what we think, and we still study it. We have immediate one due to stress, and we have over time stress relief and oxidation. And I want to thank my colleagues, the colleagues from Rotem Industry, Shachaf and Adam, which are engineers there, and from the NRCN, Don Shmulik for scientific support, and Avi and Meir for technical support. Thank you very much.
Okay, thank you very much. Are there any questions for Sharon? I have a question. I'm wondering whether you can perhaps mention what are the plasma species that are produced in your discharge, and what actually happens when you apply bias? In other words, what species are coming to the surface, and what are they doing in order to improve adhesion?
Okay, so we are using argon gas, and actually in the plasma we have also argon ions. So you're talking about the substrate, right? So
Yeah.
when we increase the bias, more argon ions will go to the substrate because we have a negatively biased voltage. And when we are doing it, so until a certain point, what we do, we also apply energy to the surface. So until a certain point, we get more dense or denser substrate. From a certain point, argon ions will enter the surface, the coating, and will cause ion pinning, and then stress inside the coating. And this stress make the coating weak and damage the adhesion.
Okay, thank you very much. Kindly take down your shared screen.
Yes.
And now I will try to share my screen, if I manage. Okay, we are here. And we'll now start our panel discussion, Plasma for a Greener Earth. I welcome all of our panelists that include Nino and Hank, Asher Yahalom and Amnon Fisher, and I put them together in a group because basically all of them will be talking about, I think, the #1 big issue that plasma can help for a greener Earth, namely in energy generation. And then the second group includes Sharon, who just spoke, Michael Kadar, Joe Lefkowitz, and myself. And I think we will talk about applications which are much more down to earth, and some of which are already being used. So I'll call on everyone in this order. I'll take my screen down and everyone can share their screen for just a 1-minute quick presentation to give an opinion about how plasma can help for a greener Earth. So first of all, how do I do this? I stop sharing. And Nino, please take it away.
Okay, I'll share my screen here for a second. Let's see. Yeah. So I think you can see this.
Yep. Oops.
Doesn't matter. So
Looks good.
This is a one slide, and I thought I put it in terms of what we can do going forward and how far we'll be in terms of initial fusion energy. So for starting with the talk I gave, I would say there are now plausible paths demonstrating 10 megajoule fusion yields near term, 20 to 40 megajoules with an upgraded NIF facility, which is approaching the IFE relevant fusion energy to laser energy gains needed of greater than 50 to have a viable economic. But the problem is, of course, you have to do this at high rate. But anyway, the plot on the left basically shows in red the N2108 where we are now. The curve is a theoretical curve if you keep increasing the capsule size by going to more efficient Hall arms, larger energy. So you go up this curve like this. See, we're on the steep part. So you can get to 20 megajoules. If you can also increase the compression that I talked about, which is a tall order for diamond, but maybe you can use plastic, then you can further increase the burn rate and the burn up fraction, which goes roughly as rho delta R. So it's plausible with a larger NIF laser, you could get to 20, 40 megajoules. So this provides impetus for further development and study. We've shown that there's a feasibility here, which was always in question, of course. Is there something really unknown? But then what does IFE provide us? Well, it has the advantage of separability of components. And that's really the main one, because what we need is a high rep rate, more efficient, as we talked about, 10% versus 1% wall plug efficiency for the laser. Modular 10 kilojoule laser units. And there's actually, I give you some references of work that was done on that under the guise of the LIFE program we had. There are other schemes like shock ignition, magnetic inertial, which could actually make things a little more efficient by driving it slower, more mass slower, but then igniting it using a strong shock at the end. And the magnetic inertial, of course. There are also potentially other useful nuclear processes you could study if you get things hot enough. Some of the aneutronic processes with other materials. But in the end, you have to also have mass-produced economical targets because you have to feed them in 10 times a second. And then here I put down what DT fusion on neutrons gives you. Just remind you, 10 to 7 more energy liberated per fuel mass in fossil fuels. You breed your own tritium using lithium black, and deuterium comes from the oceans. You can produce shorter radioactive lifetime byproducts if it's pure fusion. If you use a fusion fission blanket, you could give 4x higher gains since fission gives you more energy per fission than fusion, and can be used to breed fission fuel, which could be useful for other systems. So that's basically what I think it buys you. But
okay, Nino, I think we have to stop you there. We're
I'm
run out of time here.
Yeah.
So kindly unshare your screen and let's move on to Hank.
Yeah.
Okay, just a minute. That's it. Okay, so this is, can you see this?
Yep.
Okay, so, all right, so this is just something about fusion energy in general, much less technical than we just heard. Obviously, fusion is very important it's a safer way to produce nuclear energy than fission. You don't have any greenhouse gas. You effectively have an infinite fuel supply, so it really solves a lot of problems. So I'm just showing you some pictures here of, first of all, on the left side are the two leading candidates so far. NIF, we've heard about. ITER, I mentioned. So, and then on the right, I have two of the newer things. One is called Spark, which is a high field tokamak, and the TAE experiment. Okay, so just a few comments on it. NIF has produced fusion power, but it's not net power. And as we just heard, there's still a long way to go before you can make a practical reactor. You have to have a more efficient laser. You have to have a faster rep rate. Plus, I'm sure, many technical details that have to be solved. ITER is on a kind of slower time scale. It's under construction now. They'll have their first plasma probably in 3 or 4 years, but then they won't even start getting real significant energy production for another 15 years. And that, again, won't be net energy production, which was a recent scandal that came up in the media. They kept saying they're going to make energy, but in fact, when you take into account the stored energy that you need, it's not net energy production. But anyway, there'll be a pathway, I guess, to scaling that up. There is a pathway to scaling that up. But the new feature of fusion energy is that there are all these startups now. So I just showed you a picture of Spark, this tokamak, the TAE, which is colliding field reverse configurations, Helion, which is another like TAE in a way, which was in the paper because they raised a lot of money. ZAP is a kind of Z-pinch, flow stabilized Z-pinch. There's Zeno fusion, fusion energy. So there's a bunch of them actually. Some are they're all promising to be showing fusion in a shorter time scale than these big experiments.
Okay, Hank, I'm
But of
going to
course, they're
stop you
higher
there so
risk.
we can
They're
move
higher
on.
risk. You don't know, and I'm not sure if they're good investments. If anyone wants to invest in them. Okay. that's
Okay,
it.
thank you, Hank. And if you could take down your screen,
Yes. Okay.
I'll move on to Asher Ya'alom. Go ahead and share your screen or talk without a screen, whatever. Asher Ya'alom from Ariel University. Okay, we see it. Go ahead. You have to unmute.
Maybe you want to see me also.
Yeah, absolutely. Go ahead. Take it away, Asher.
Okay. So, yes, fusion is the holy grail of green energy production, as Hank said. And I think one of the main problems is stability. You need to get this hot plasma for enough time to produce energy, and then you can get more energy than you consume. Now, when we talk of stability, I mean, for simple systems, there are simple solutions, right? If you ride your bike, you just need to give it enough angular momentum to the wheels, and then it becomes stable. In plasmas, you have non-trivial topological conservation laws, which also cause stability. And that may be the reason why stellarators are going to win the fight against tokamaks. Hong Kim and myself described several new topological constants in a recent paper this year. So you have the reference. And the problem is, of course, that those topological constants are only ideal constant in ideal fluids. So the question is, what does non-ideal processes do to those constants? And I'm talking about resistivity, viscosity, heat conduction, and other transport phenomena. And luckily enough, some of them are conserved even in non-ideal cases. For example, magnetic ericity is not affected by viscosity or heat conduction. And that's why it has a very profound effect on turbulence in magnetohydrodynamics. So there is much to study, and we are studying this, and maybe we can suggest something that will make those devices more stable and therefore smaller and more efficient. Thank you.
Okay, thank you. Amnon, you're up. Shall I put your slides up, or you think you can do it yourself? You have to unmute. Unmute, Amnon. Turn your microphone on, Amnon. We're not hearing you.
Amnon, just do unmute on your screen. Yeah.
Okay, good. Shall I put your slides up, or do you want to?
Yes.
Can you put my slide up?
Yes, I can, I think. I'll try. Hold it. Share screen. Ta-da, ta-da. Okay, you're on.
Okay. I will read what I said here. The controlled thermonuclear fusion is a plasma-based device. It hopes to produce unlimited energy with little radioactivity and, of course, no CO2. In my opinion, no commercial thermonuclear energy will be available in the foreseeable future. Too many physical engineering problems have not been solved yet. The high Q required to make commercial reactor makes this goal very difficult. The only way out of these difficulties is to use fusion as a fusion-fission hybrid. Fusion devices, even with Q less than 1, can supply enough neutrons to generate fission. And it can be done in a depleted uranium and not in thorium. And if you have enough neutrons, you can even burn the ashes of the byproducts of the fission. So the idea of having pure fusion to generate energy is, I don't think it's possible. It's too expensive, too complicated. And fission is a solved problem, and the society has to overcome this inhibition against fission. One last thing I wanted to say, which will affect how green our Earth is going to be. Plasma physics played a major role in the revolution of solid state devices. Without plasma etching, we would not be able to reach this fine structure. What plasma etching did is increase 3 orders of magnitude in feature sizes, even more. And that's if you take on a surface a 6 orders of magnitude. 6 orders of magnitude is a big, big difference. I used to say that a factor of 2 in technology is like a factor of 2 in salary. So a factor of 6 in the exponent is a big, big number. So this plasma application, which is not in the limelight, it will outshine, in my opinion, any other plasma application, including fusion, for many years to come.
Okay, thank you very much. Now we've heard about how fusion and plasma fusion will save the world, but not this year, not next year, maybe, probably not in my lifetime. Let's hear about some plasma applications that can make an impact on the greenness of the Earth even today. I forgot the order, so I'm going to try to wing it here rather than taking time to share a screen. And I'll call on Michael Kadar first.
Okay, let's see.
You may share your screen if you have slides.
Well, yeah, I do have just one slide here.
Good.
I guess you can see it. Thanks, Rowan. So I just will bring one particular angle to that, and it will be in my talk this afternoon. But the idea that was not much explored in low temperature plasma anyway is the possibility of creating what I call adaptive plasma. So that might be very efficient way to create chemical reactivity. Not that it will be readily available tomorrow, but there is a lot of efforts in that respect. And the point here is that uniqueness of the plasma is really its ability to change the composition on demand. And I give you an example here. This is in my world of, say, in developing adaptive cancer therapy. Then if there is a way to monitor or respond in real time, so then that can be incorporated in the through the feedback in creating very targeted, very specific reactivity, and that's completely different from, of course, simple chemical reactivity that kind of set in stone, and there's a lot to be explored in the direction, and I invite everyone to my talk this afternoon, for that matter. Thanks. I think we are frozen.
Ray, you're on mute.
I can stop sharing my screen to advance this. Ray, you on mute.
Ray, you are on mute. Nobody can hear you.
Okay, sorry. Sharon, you're up. Thank you. Sharon, you have to unmute. Unmute, Sharon.
Now,
Good.
Okay, yeah.
Full screen if you can. Great.
Yeah. I will talk about plasma coatings for a greener Earth. So highly significant issues concerning a greener Earth include the energy conservation and environmental protection. Tailor-made coatings are of great importance for saving energy, and they have also environmental benefits in different applications. For example, for tools and machine components, by reducing wear and friction, for solar cells and panels, by reducing anti-reflectivity. So more energy with the same amount of sunlight can be produced. And also for a low emissivity windows by saving energy in buildings. The main plasma deposition techniques that are used to do these coatings are magnetron sputtering, cathodic arc for hard coatings, more for wear-resistant coatings, and plasma enhanced chemical vapor deposition that provide deposition at low temperature, better adhesion, and dense and uniform coatings.
Okay, thank you very much. Joe, you're up.
Yeah, I'm doing it.
Unshare, great. Joe, unmute. Joe Lefkowitz from the Technion.
Okay, are you seeing my slide?
Well, perfect.
All right, so I'm working on something that Professor Kedar mentioned, which is using plasma chemistry. Basically, I've been working for a long time on the relationship between plasmas and fuels for combustion. And what we've been trying to do lately is work with ammonia as a fuel. And so ammonia has the benefits of working through this general reaction, where if I burn it with oxygen, I only get nitrogen and water as an emission. And as was mentioned in the morning, in the plenary, the battery storage for energy is quite a challenge to store as much energy as we need. So chemical energy storage is quite useful. Hydrogen is very hard to store. Hydrogen is not possible for aerospace, very difficult for marine transport, but you can convert hydrogen to ammonia, and then it becomes quite viable fuel. The problem is it doesn't work well in internal combustion engines, which we have so many of on Earth, of course. So we've been working on plasma techniques using these kind of plasma reactors you can see here to change the properties of combustion, whether it's reduce ignition delays, increase flame speeds, and ignite them in a traditional sense. And we could do this by targeted electron collision reactions and then leading to a change in the mechanism of ammonia oxidation, which allows to bypass a lot of the rate limiting steps. And by doing this, the hope is that we can use ammonia as a hydrogen storage device and then use it in today's and future IC engines, whether for distributed power generation or for marine or aerospace transport. And ammonia is the second most produced chemical on Earth, with about 5% of the production rate of oil. So it's a hugely produced chemical, and it can be used from all of the green hydrogen to really make a difference on the energy economy. And
Okay,
we're trying to—
thank you, Joe. Unshare your screen if you don't mind. And we'll move on to the last contribution, namely mine. If I could just find the screen.
To hear more, my student Galia will be presenting at the poster session.
Great. Okay, here we go. Okay, can you see my screen?
Yes.
Great. So I'll just be very, very quick and talk about plasma depollution and disinfection of water and also in general of air and other materials. What we do is generate an electrical discharge, an arc discharge, pulsed arc discharge underwater. What we see here is a pulsed arc. This is generated by high voltage. What we actually do is generate it by low voltage. And this is significant in order to decrease the energy required. And here's the thing. If you have a very, very polluted process water, for example, from a chemical plant, we can use this process to get this result. Basically, you can reduce the total carbon concentration within the water from very, very high values to values which are more readily disposable by, let's say, more conventional technologies such as bioreactors. Likewise, this will kill bacteria. And the way it works is that during this discharge, you're producing UV radiation, which basically can knock out the DNA from bacteria, and radicals, in particular OH, neutral OH, which is a very, very strong oxidant, which will basically destroy the membranes of bacteria and will oxidize organic pollutants. And with this, I'm sorry, but we don't have time to have a discussion. And that was the whole idea. We all talk too much. So I apologize. I thank everyone who participated, but we have to move on to the flash session. So let me stop sharing this screen and share this. I'll call upon these presenters in this order, and I will show the screen, and 60 seconds is all I'm going to allow you because we're running overtime altogether. And after this, I'll ask for Yang Bin, who didn't send me his slides, to present his slides, but I'm telling you 60 seconds only, including putting up your screen. So let me begin with Yitzhak Bellis. We'll talk about zirconium thin film deposition using a hot refractory anode vacuum arc. Yitzhak, unmute and give us a quick presentation. Unmute. Yitzhak, you have to unmute. Turn your microphone on.
Sorry.
There you go.
Our poster material presents investigation of zirconia thin film deposition by hot refractory anode vacuum arc. In this plasma source, the plasma jet deposited the cold anode in the initial stage, together with macroparticle, but this time the hot anode re-evaporated the material, and the macroparticle directly converted it to the plasma. The plasma expands radially to the substrate, and the deposit the substrate with deposition rate about 1 micron per minute. So,
okay, thank you very much. The next flash talk by Mr. Mahler, generation of supersonic water jets by underwater electrical explosion of wire arrays. Go ahead, unmute and tell us what's going on.
Thank you, Ray. Hello, everybody. So I will present in my poster the generation of supersonic water jets by underwater electrical explosion of symmetric wire arrays. In my poster, I present the experimental and numerical results of high velocity water jets, which could be used for the study of high energy density physics. Both water jets reach velocities of up to 4 kilometers per second. And also recent numerical modeling also suggests that the generation of these high velocity jets could be the result of accumulation effect happening in the axis symmetry when shock waves and water flow accumulates. Thank you.
Okay, thank you, Daniel. Next, I call on C. Shen, also from the Technion, on the energy distribution and nanosecond pulse high frequency discharge ignition.
Hi, hello everyone. So here's a preview of my poster. My research focused on the application of nanosecond pulsed high frequency plasma discharge as ignition method for high-speed combustion. So two big challenges we face in high-speed combustion is one, short flow residence time, and high turbulence induced quenching. So we found a promising result using the pulsed plasma discharge. And then here's a picture of our ignition tunnel in the middle and some Schlieren image from the ignition kernels and their different discharge conditions. So in our experiments, we went up to about 20 kilovolts discharge voltage, 50 kilohertz, and then up to 40 pulses. The pulse width is about 10 nanoseconds. So if you want to know more about the details, and please come to my poster session, I'll be more than happy to tell you more about it. Thank you.
Thank you so much, Sishen. And now I call on Galia Feingold, also from the Technion, enhancing ammonia combustion with plasma created species.
Yeah, so Joe gave a very nice introduction to this just a few minutes ago. I'll go a little bit more into detail, but I just want to say, so we can't burn fossil fuels anymore. That's becoming pretty clear. Solar energy is cheap. It's a mature technology. And the problem is how to store it and how to have long-term storage, how to make it scalable and how to make it flexible. That's why we're looking at ammonia as a fuel. It's a hydrogen carrier. And specifically the research that I will be presenting today is how to improve combustion with just two of the stable species that we can produce in a plasma, which is hydrogen and ozone. And we got like very like orders of magnitude better results with just a little bit of additives from plasma. So that's what I will be showing, these very exciting results.
Okay, thank you so much.
Thanks.
And see, the next one is by Itamar Cohen from Tel Aviv University. Laser wake field acceleration from nebular shaped plasma. Itamar, take it away.
So today I will present our electron acceleration method using laser plasma interaction. And we use an ultra short 25 femtosecond high intensity 20 terawatt pulses. And here in our acceleration scheme, we explode a submicron foil into an underdense near critical plasma that is of a few tens of microns in length. And the high intensity laser interaction with this plasma then drives plasma waves known as the wake field, which electrons can be accelerated in. And in our case, the acceleration results in multi-MeV energy range and very high conversion efficiency, which can be used, for example, for photonuclear reactions. And in my poster, I will show some experimental results of the measured plasma plume and the accelerated electrons and discuss some of the models we developed for the interaction.
Great, thank you very much. Yang Bin, Zhang Bin, would you like to put up your slide? And unmute, please.
Yes. I need to share my screen, right?
You do.
Okay. So just a minute. Hello, everyone. Today I want to give a poster named Quantum Electron Optics. We focused on the interaction of the shaped free electron wave packet interact with light or with matter based on the quantum electron wave packet duality property. For the interaction with light, we we investigate in the inverse Smith-Passeur setup and modulated the electron with a laser, and then the electron would interact with the plasma induced by the laser on the grating. And we find that the electron would behave like the quantum property when the wave packet size is much smaller than the laser period, and behaves like a classical acceleration behavior when the wave packet size is much larger than much smaller than the laser period. Also,
okay, that's all for right now. For more details, please go to Bin Zhang's poster. I want to thank everyone for their presentations. And from here, please go back to the plenary session. And then after a short break, please go and visit the posters. The posters are really great. We could see a preview just now. And we'll probably meet up in one of the poster rooms. You go to the main program on the website, and it'll have links to each of the posters. So see you all there. Thank you so much for your participation. And it's just great to see all of you here together. I'm looking forward to next year that maybe we can meet in person rather than by Zoom. Bye.